All right, so let's talk about digital signals. If you've watched the other video before this on analog signals, you should have a pretty good understanding of the signal, or a basic understanding of what that analog signal will be directly related to understanding digital signals. So the first thing, let's take this one step at a time, because we're dealing with signal processing. So it's going to go into digital audio and how it interprets it and uses it. So we're going to go into that, just some very basic concepts. And like all the videos that I make, I very much expect that I try to use like Wikipedia as a great place, and you can go to these pages and you can go to the links on there and branch out, branch out your knowledge to the level that you think you're going to need for your understanding for what you're trying to do. But a basic understanding is good to have no matter what level you're working at, digital signal processing or music production, working in this environment. So let's look at a digital signal. First of all, you understand what an analog signal is now. So what a representation of that is a digital signal is a sequence of discrete values. So instead of continuous, that it is discrete. So what is discrete? Discrete, very simply, means it's in a time series through time. It's a sequence of quantities. And when we're talking about audio, we're talking about a sequence of amplitudes. More times than not, it's a sequence of points in time at different amplitudes. And basically most of the time that's the very simple understanding of it, so that it can relate it directly to that continuous analog signal that's varying continuously in voltages. That's a representation of the continuous change in rarefaction and compression in the analogous sound that it's trying to capture. So I hope I made that very simple, so that, that can be very complex, and I very much do, advise you go to some of these pages and branch out your knowledge a little bit, but that's a basic understanding. So if we come back to the digital signal, that's a real basic understanding of it. So when we're looking at digital signal in electronics, most of the time you're talking about a pulse train, and a real simple understanding of that is, if you went back and watched those videos on sound and waveforms, a square wave, that basically what's happening there is you are going to get a pulses of certain levels of amplitude that are set over time. So you've got, and they're going to be pulses of amplitude. There's not, and it's real simple as far as that basic understanding. That can be very complex for how many different ways that can be put together. But basically, digital electronics work with digital pulse trains that are, set in time, over time, pulses of amplitude. And the basic understanding of it is that simple. So that's in digital electronics, that, that's the basic concept. In signal processing, that you're dealing with, most of the time when we're dealing with this, is pulse code modulation. And so, that's another concept we'll get to in a minute. But it's basically a set of values over time. So, and it's not continuous, but from understanding the analogous signal, that it's trying to represent that in set periods of time along the timeline that are sampled of the decibel value, or the voltage value, either way that you want to look at it. In actual electronics, it's going to be the voltage value. And quantified, so, quantification. Let's take a real quick look at that. Quantization can be very complex, but let's look at this as simply as possible, and you can always branch out your knowledge, but just a simple understanding is that it's rounding and truncating. That means that each one of these samples that are on here, that for it to create each one of these samples for quantization, it's captured these samples and then it's rounded it to as close an approximation of the original analogous signal and truncated any information. And truncating just means it's cutting off information, which is basically part of the rounding process. So it basically, it tries to approximate it with quantization, and that can cause quantization noise and things like that, which basically boils down to it's not an exact representation of the analogous signal and issues that can occur from that. So that's a real basic understanding and a very simplified understanding of what exactly is happening there. All right, so the pulse code modulation very simply is what we've already talked about, is capturing points in time of your analogous signal and their amplitude, and then quantizing them. And we've talked about the basic understanding of what that is. So that whole concept, linear pulse code modulations and pulse code modulations, I do recommend that you Google them and read a little bit about it, but that's the basic understanding of what's happening there. Okay, so you have a basic understanding of what's happening with the digital signal, and you should be able to relate that fairly easily to what's happening, what's coming from the analog signal and what's happening there. So the difference between them. So let's say so the next thing would be to understand is what's happening if you've got all these samples that have been quantized, and is it going to just put pulses in your audio? Is that the way that works? Well, no, it's not. What happens is a process called interpolation. Now, interpolations, again, can be very complex, so I'm going to give a real simple understanding of this. Different types of interpolations will do different things, but the basic understanding of interpolation is you have one captured sample here, that's a capture of the analogous signal that you want to represent in the digital realm. So you've got one here and you've got another here. Well, how do you connect them? So basically you have to do a process called interpolation. That way that it's going to represent it as continuously as possible and as close approximation to what the analogous signal was. Again, that can cause some issues. The same thing as quantization error can, because it may not be exact. The interpolation, the line that's going to connect this to there, may not be the exact waveform that was the analogous signal. It might not be. It's a guess. There is no way to actually know exactly what it is. So it's always worked out to a best guess. And so the way that most of the time that's dealt with is the more samples, the better. That way the interpolation between samples is smaller and smaller and smaller. That way you have a better representation of what's happening between the samples that you captured. And that's a very simple understanding to understand the process that's happening. So let's look at a next part. All right, so the next aspect of it is how is it storing that? So it's not continuous. You can't sit there and sing and then rewind a minute and then sing again. So how's it doing that in the studio? So with your digital signal. So basically what it has to do is it has to store it as binary information. So I would suggest you Google binary information, and some of it can be kind of complex, but a basic understanding of it is that a lot of times, the basics of what it is basically it's a number that represents that amplitude, and it's that simple. Because if you understand how a complex waveform works, that basically it's a series of amplitudes, plus and minus, in positive and negative values in voltage is how it works out, correct? From what I was talking about the analog signal. So it has to store that. And it'll store that as a signed or unsigned number. Signed or unsigned, it just basically means, is it going to have a negative value and a positive value, or is it just going to have a positive value? And it's that simple to understand. That can get very complex, but that's a basic understanding of it. So basically what it has to do is store it as just binary information. So let's take a little look at that. All right, a very simple understanding. Let's look at a very simplified look at binary information. Okay, this is the binary information. All right, so the actual values, let's say you set up a row that's got 1, 2, 3, 4, 5, 6, 7, 8 blocks to store a binary information, and you assign them 1, 2, 4, 8, 16, 32, 64, and 28. Those numbers. So then, you know, what's going to happen is that these are going to have numbers up here. They're going to be like light switches. So you turn this one on and give it a 1. This one you don't turn on, so you leave it as 0. So you're going to have 128 as a value that's going to get added in there. There's no 32. You left that light switch off. 16 you turned on, so 16 is going to drop down there. 8 you left that light switch on. 4 you turned that light switch on, so 4 is going to go down there. 2 you turned that light switch on, so 2 is going to go down there, and so on and so forth. These are like light switches that you turned on and off. So with this value here is going to be the binary byte. Okay, so byte is, you know, 8 bits, correct? 4 bits and 8 bits. So now you have that binary algorithm set up. So now you have a total here, and you add those up, and that will be the number that you'll be looking at that'll be stored as the amplitude of the sine wave or the signal that you're processing. Does that make sense? And you can look that up. It can get a lot more complicated than that, but that's just the basic understanding of how it's storing that. So then it'll store this number at that point in time and added up these values here as the amplitude of the waveform at that point in time. And it's a little more complicated than that, but that's a real simple understanding. Next, how it's storing it. So you'd be talking about formatting, which can be very important when you're doing mastering. So formatting, what you've got, we've already looked at the binary data. So when you're looking at the formatting, it's going to tell you the sample size, 16-bit, that's how many bits that we just talked about, that little light switch is on or off, how big the number is to store it as accurately as possible. 32-bit, huge number, or 64-bit, really huge number that can be very accurate, as far as what the amplitude is. And that's a real simple concept to understand. And in the formatting, it's going to be big or little endian, and we won't get into that too much. But the actual bits, you understand what's going on there, signed or unsigned, whether it's going to have positive and negative values or not. Number of channels, sample rate, how many samples per second that it took, and floating point or not. So those are this can be very complicated, and I did a lot of study on this, and I'm not going to get into it that deep, but basic and understanding of what it's trying to do so it can just represent that number. So how do you see it? Okay, so very simply, the other thing that you're dealing with is no matter how you're seeing it in the studio, whether you got an MP3 or it's on your CD or wherever it's at, and it's in the studio, that it's been formatted, okay? So, and then it doesn't really matter whether it's a normal WAV file or an MP3 or what it is, that it has been formatted or you wouldn't be able to read it. It's been converted in some binary information so that it can, interpolate those, that binary information in those samples, quantize it, and then interpolate it so that you can hear the audio and work with it and edit it and do whatever you're going to do to it, correct? Okay, so that's a real simple concept to understand. So how do you do it? You put it in different types of formats. Now, I'm going to leave it up to you to go. You can check out any kind of formats you want. But I just kind of want to look at a format here so you can understand a little bit what's happening. So, what's happening here? I've got this hex editor called Hex Editor Neo. Now, I've put it in here, this WAV file, and it's going to tell you what kind of, the WAV header. It's going to tell you what type of a file it is. It's a WAV file, whether it's an MP3 or whatever. It's going to have all kinds of information on, there can be all kinds of information that you can put into the formatting that describes the piece of audio. All kinds of information, but real simple. I'll go down here and tell you number of channels, samples per second, average bytes per second, bits per sample, 16-bit, 32-bit, whatever. And then you can go down and look at the samples. So this is unsigned. So we already talked about that. So this is giving you the values with a combination of these of what the decibel level is or what the voltage level is on each one of those samples so that it can interpolate those and then put those in onto your piece of audio so that you can see it in your DAW to work with, and that's how it's stored. And it's that simple. That whole concept can be very, very complex, but that's simple explanation. So I hope that I addressed digital signals to where you could understand them a little bit better, and you dig around and learn some more. Peace, hope, love.